One of the goals I've set for this course is to drive the learning through our labs, the experiences where we model and do some calculations to understand all kinds of issues about environmental controls in the built environment. Yeah, so in order to do that, every week or every module, I need to prepare you for the content that we're going to be working with. And sometimes it doesn't quite dovetail perfectly with the layout of the course as far as subject matter. So this graphic just kind of shows that. This is the course requirements that we are mandated to cover in Environmental Controls 1. And I say mandated, but it's really just the groundwork to prepare you for studio experiences and equip you to deal with your projects in studio. So it's all good. But anyway, there's a bit of a picking and choosing to bring everything together to fit into your lab. In this case, we've already covered solar orientation, but we do need to start addressing this idea of human comfort in the built environment and why we need to temper and control the temperature in a space. And then we also need to introduce some ideas about heat loss and other ideas of heat transfer within a building envelope. So with that said, let's just start with a little bit of discussion about human comfort in a built environment. And we're all a bit familiar with that, obviously, because we're all humans. We feel comfortable in certain settings and not comfortable in others. We have a relatively narrow temperature range that we find comfort in. So this idea of human comfort is really based on about these 6 items: how much we're doing as far as activity goes, whether we're playing a sport or sitting and reading, how much clothing we have on, how much air is moving, whether it be the wind blowing or a fan or just the motions of air in a room. Humidity, one that we don't think about all the time. Temperature, one that we always think about. And radiation, the ones that we're aware of when we're in things like sunshine or near fire. So all of these things act together to create a sense of comfort in a room. And if we have a lot of airflow, we may want to have a warmer temperature. And conversely, if it's colder, we may want to reduce airflow to keep from chilling ourselves. So all of those things working together, we have formulas for doing that. So let's just quickly kind of think about this before we go on to the next slide. So here we have a person exposed to the radiant heat of the sun, feeling warm. Water is always evaporating from our skin. And if the wind's blowing, it drives that evaporation and makes our skin feel cool. It also blows the heat. If there's wind moving, it also blows the heat away from our body. There's a little thin film of warm air that surrounds our body. And when there's wind blowing, we get an effect called wind chill, where that warm barrier layer is removed. And we can mitigate that with the addition of clothing, um, and so forth. So I've added a couple of other graphics. This is just to reinforce that idea of a radiant heat being warmed in a cool room by a fire that's far distant, because the method of heat transfer is radiation, just like light moving across the room. You only feel it when it strikes a surface and warms it. And then bringing it all together in this idea of thinking about how this all of these factors of heat exchange between the human or the person and the environment affect thermal comfort when we're talking about being in an enclosure. So in this case, we have a graphic of a house, the idea of the sun shining in, creating radiant heat maybe from the floor, it having a natural humidity to it, a temperature, and all of these things having to be in some kind of a homeostasis within a certain range to create what we would feel is a comfortable environment. And fortunately, all of these things, like I say, play off of each other, but we have ways of calculating and assigning values so that we can scientifically present the idea of being within a range of human comfort. So here's a tool. If you go to the slideshow, it's hyperlinked. It'll take you to this exact calculation. I'll click on it just so you can see. It's a thermal comfort tool. You input all of your settings, and it gives you a range of human comfort according to certain kinds of standards. And we'll go back to the presentation here. Oops. And I want to review kind of the inputs that'll go into this calculator. Mean radiant temperature. The mean radiant temperature is the temperature of the surfaces that are around you. temperature of the wall. The wall is exposed to the outside, so it might be warmer than the interior temperature. The airspeed, the air moving by you, the relative humidity in the air, higher humidity, less heat loss, um, metabolic rate, and measured in METs, which means how active the person is, and then the clothing level. So all of these factors can be placed into a calculation, and a psychometric chart is developed that allows you to observe a defined amount of comfort zone. And these vary with different kinds of standards. The one I picked that's I'm relatively familiar with, and you would be too, as we move forward, is ASHRAE. I believe it's American Society of Heating, Refrigeration, and Air Conditioning Engineers, and they have a standard for human comfort within a built environment. And if you meet this standard, then you have met the goals of your design element. So anyway, you have the input of the air temperature, the radiant temperatures of the surfaces, whether there's air moving, what the relative humidity is. And you'll notice some of these are actually describing the task. So in this case, we have typing, and it's 1.1 METs of energy is expended. Clothing level, typical summer clothing, zero point 0.5 clo imposed value for clothing. So these are wonderful tool to develop this idea of thermal comfort in an environment. And obviously, we would like to have an optimized thermal climate all the time, but many of these factors we don't necessarily always have control over, whether it be the relative humidity in the space, how much work or activity any individual in the space is doing, how they're dressed, and so forth. So I'm going to wrap up that idea just to get you started on this idea of human comfort, and just present one other piece of information, not specific to the idea of human comfort, but how we measure that idea of relative humidity. And relative humidity is how much moisture the air can handle at a given temperature. And there's a test called a wet bulb, dry bulb, and it's something an architect should be familiar with. The idea is that we have these devices that have thermometers on them, and they can be slung around. They have a handle on them, and you have a dry bulb thermometer, one without a wick on it, and then a wet bulb, one with a wick, that's moistened. And as you move it through the air, water evaporates off of that. So we have this combination of wind speed and evaporation, cooling that thermometer down the wet bulb. And the difference between those two helps us establish what the relative humidity is. So this is something that you would be required to kind of understand on how we come up with this idea of relative humidity. So I'll end this part of the presentation and we'll pick it up in another clip.